So in part 2 of section 4, we're going to take a look at factoring when a is greater than 1 for trinomials, and then we'll also talk about a couple special cases when it comes to factoring. So we already talked about factoring out of GCF, factoring trinomials when a is 1, and then combining those methods. So let's start with factoring trinomials when a is greater than 1. So these problems are a little bit more challenging because not only is a greater than 1, but there's also not going to be a GCF. So for our first example here, we have 6x squared plus 37x plus 6. And I'm actually going to do all of these examples using something called the box method. So how it's going to work is we are going to set up a box and we're going to put 4 squares in that box. The top left corner is always going to be your x squared term. So I'm going to put 6x squared here. The bottom right corner is always going to be your constant, which in this case is going to be 6. Now what I'm trying to do is I'm trying to figure out what those other two terms are, which are the terms that are going to add to 37x. Now where it differs is I'm not looking for the numbers that multiply to 6 and add to 37 because obviously they don't exist. So what ends up happening when you distribute is you actually end up multiplying and you, so like when you distribute your x term, when you put it in your parentheses, instead of having x times like 3 to get 3x, whatever, I'm going to have a number in front of x other than 1. So like 2x or 4x, and that ends up multiplying to my constant. So I'm actually looking for numbers that multiply to 36. So you always have to do a times c when you are factoring trinomials when a is greater than 1. So I'm actually looking for the numbers that multiply to 36 and add to 37, which are going to be 36 and 1. So my other two boxes, one of them is going to be 36x and the other is going to be 1x. And it doesn't matter which box I put them in, it's just one of them goes in one box and the other goes in the other. Now what I'm going to do is from each row and each column, I'm going to factor out the GCF. So 6x squared and 36x, their GCF is 6x. 1x and 6, the only thing that they have in common is 1. Now I'm going to be going down. 6x squared and 1x, the GCF is x. And then 36x and 6 have a GCF of 6. So the nice thing about the box method is I can now multiply what's outside my boxes and I should get everything that is inside my box. So 6x and x give me 6x squared. 1 and x give me 1x. 6x and 6 give me 36x, and then 1 and 6 give me 6. So my final answer is 6x plus 1, x plus 6. Let's do another example. So 2x squared minus 5x minus 3. So I'm going to create my box. I'm going to put 2x squared in my top left. I'm going to have negative 3 in my bottom right. So I'm looking, when I do a times c, I'm doing 2 times negative 3. I'm looking for the numbers that multiply to negative 6 but add to negative 5, which is going to be negative 6 and 1. So I'm going to put negative 6x and 1x. 2x squared and negative 6x have a GCF of 2x. 1x and negative 3 have a GCF of 1. 2x squared and 1x have a GCF of x. And negative 6x and negative 3 have a GCF of -3. So I get 2x plus 1, x minus 3. Next example, 12x squared plus 17x plus 6. I'm going to have 12x squared in my top left, 6 in my bottom right. So 12 times 6 is 72. So I'm looking for the numbers that multiply to 72 and add to 17, which is going to be 9 and 8. So I'm going to have 9x and 8x. 12x squared and 9x have a GCF of 3x. 8x and 6 have a GCF of 2. 12x squared and 8x have a GCF of 4x. And then 9x and 6 have a GCF of 3. So we'll have 3x plus 2 times 4x plus 3. And very similar to when we were doing section 1, I can always double check that I have factored these correctly by distributing. So if I want to check, I'm going to multiply. I get 12x squared plus 9x. And then I get plus 8x plus 6, which gives me 12x squared plus 17x plus 6. So I know I've done it correctly. Last example from this method, 4x squared minus 4x plus 1. So I'll put 4x squared in my top left, 1 in my bottom right. So I'm looking for numbers that multiply to 4 and add to -4. So this is a little bit different than the ones that we've been doing. So anytime we wanted to multiply to a positive, I was just like, it was 2 positive numbers. But in this case, I want to multiply to a +4, but I want to add to a -4. So there is only one way to multiply to a positive and add to a negative, and that is if both of your factors are negative. So there are 2 ways to multiply to 4, -1 and -4, or -2 and -2. So both of those multiply to +4. Now the only one that is going to add to -4 is the -2 and the -2. So I'm going to put -2x and -2x in my boxes. So 4x squared and -2x have a GCF of 2x. -2x and 1. So whatever the sign is of your x term, when you're looking at the row or the column that contains your x term and your constant, you have to take the sign of the x term. So -2x and 1 are actually going to have a GCF of -1. 4x squared and -2x have a GCF of 2x, and -2x and 1 have a GCF of -1. So I'm going to get 2x minus 1 in both sets of parentheses. So it's 2x minus 1 times 2x minus 1. Another way you can write this is because it's the same thing multiplied to itself. I can also write this as 2x minus 1 squared, because I'm multiplying something by itself. Both of those are correct answers here. So now we're going to talk about some special case binomials. So these are specifically binomials. Remember, binomial is 2 terms. we're going to specifically look at something called difference of squares, and then we're also going to look at sum and difference of cubes. So a difference of squares is the form a squared minus b squared. So what that means is both of the terms you have, the two terms you have, are perfect squares, but they're being subtracted. So it always factors the same way, a plus b and a minus b. So whatever your number that multiplies to give you that perfect square, it's the same thing in both sets of parentheses, just one is a plus and one is a minus. So look at some examples. So I have x squared minus 49. So two terms, and if I look, x squared is x times x, 49 is 7 times 7. So my a is going to be x, because that's my first term, and my b is going to be 7, because that's my second term. So it's going to factor as x plus 7, x minus 7. What makes these special is that when I distribute, my x term ends up canceling. And the only way for my x term to cancel is if you have two numbers that are the same, but one of them is positive and one of them is negative. Our second example, we have 4y squared minus 81. So 4y squared I can get by doing 2y times 2y. 81 I can get by doing 9 times 9. So my a is going to be 2y, and my b is going to be 9. So I get 2y plus 9, 2y minus 9. And it doesn't matter which parenthesis you make the plus and which parenthesis you make the minus, as long as one of them is a plus and one of them is a minus. All right, our next example, 12 minus 3a squared. So I'm looking at this, 12 and 3 are not perfect squares. So what I'm going to do here is I'm actually going to end up factoring out a GCF. 12 and 3 are both divisible by 3. So I'm going to factor out my 3. I'm going to be left with 4 minus a squared. Now I have two perfect squares. I have 2 times 2 is 4, and a times a is going to give me my a squared. Now, which one you identify as a and which one you identify as b is important. A is always the first one. So my a in this case is 2, and my b is going to be my variable a. It does matter how you write a difference of squares, because the order of subtraction does matter. So this is going to be written as 3 times 2 plus a, 2 minus a. So the 2 plus a I can technically write as a plus 2, and it's the same thing. But 2 minus a and a minus 2 are not the same thing. So it does matter where my variable is and where my perfect square number is when I factor. Next example is y squared minus 1/25. So y squared is y times y. 1/25 is a little bit harder. I know 25 is a perfect square. It's 5 times 5. So it can also work in fractions. So 1/5 and 1/5. So my a is y and my b is 1/5. So it's going to factor as y plus 1/5 and then y minus 1/5. We won't really do a lot of examples where you're factoring a difference of squares where there's a fraction, but just wanted to show you an example. Last example, x squared plus 25. So even though x squared and 25 are perfect squares, the thing to notice here is that we have a plus sign instead of a minus sign. So this is actually not factorable. Because it's a plus and not a minus. Everything we've just done only works if it's a difference of squares. So it has to be subtraction. If it's addition of perfect squares, they're actually not going to be able to be factored. Right, so the last special case is something called a sum and difference of cubes. So unlike difference of squares, where we could only subtract two numbers that were perfect squares, if you have two terms that are perfect cubes, so like 2 times 2 times 2, which is 8, you can actually do that for sum and difference. So those can be added or subtracted. And there is a very special formula that we use, just like with a difference of squares. So for the sum of cubes, you have your two terms, a cubed plus b cubed. My first set of parentheses is just going to be a plus b. Then my second set of parentheses ends up being a trinomial of degree 2. It actually factors as a squared minus ab plus b squared. And this trinomial is actually not factorable. So that's why you're going to have a binomial and a trinomial that multiply together. The trinomial that you get is never going to be able to be factored. For my difference of cubes, so a cubed minus b cubed, my first set of parentheses is going to be a minus b. And then it's a squared plus ab plus b squared. So very, very similar formulas, just slightly change a plus and a minus between the two. And again, for the difference of cubes, that trinomial you get in the second set of parentheses, not going to be able to be factored. Right, so let's look at a couple examples. So first one I have is x cubed plus 125. So x cubed is x times x times x. 125. If I want to find the number that multiplies by itself 3 times to get 125, I'm not going to do 125 divided by 3. Because yes, 25 times 3 is 125, but I'm looking for the number, but 25 times 25 times 25 is not 125, and that's what I'm looking for here. So the number that you multiply by itself 3 times to get 125 is actually 5. 5 times 5 times 5 is 125. So my a here is x, and my b is 5. So when it factors, I'm going to have x plus 5. And then I do a squared, which is going to be x squared, minus a times b. Now instead of writing x5, I'm going to write 5x. And then plus b squared, and 5 squared is 25. And that's going to be my answer. The last example, I have 27x cubed minus 1. So 27, 3 times 3 times 3. So I'm going to have 3x, 3x, 3x. And then 1 is just 1 times 1 times 1. So my a is going to be 3x, and my b is going to be 1. So when I factor it, I'm going to my first set of parentheses, a minus b, so 3x minus 1. Then I want to square a. So I'm not just squaring the x here, I'm also squaring the 3. So it's going to be 9x squared plus a times b, 3x times 1 is 3x, plus 1 squared, which is 1. Let me know if you have any questions about using the box method to factor a trinomial when a is greater than 1, or our special case binomials, which is our difference of squares, our sum of cubes, or our difference of cubes.